yeah, let's go about it. The plan for today is, in the previous streams and videos, I've used some concepts which are essential to Haskell programming, which are functors, applicatives, and monads. And these things are type classes. Now, type classes are something like your Java interfaces or PHP or whatever language you use, where you only export a contract of what functions you expose to a client API, like only export functions to a consumer. And in this video, we're going to re-implement some of these type classes. And we do this by creating our own list data type in Haskell and our own maybe data type. And I hope to have some questions for the chat and we can explore the concepts together. Now, I did say I expected some programming background, but well, Haskell is so different, you know. And I think the difference already shows in the first declarations we make in the stream. So I said we want to make our own list type, and we do this now. We start with the data keyword. The data keyword makes a new data type, essentially. And we're going to call this data type myList, and it has a type variable of A. And you can imagine this like class myList T if you are from a JavaScript, or not JavaScript, but if you're from a TypeScript or Java background. And now you cannot do much with this data type. If we try to load it into the interpreter and we use :T to inspect the type, it will say, hey, I don't have a data constructor for this type. But if we say info on the type, I hope, it still doesn't work. Okay. Can we browse though? With browse you can inspect what things you have in scope in your interpreter. And it doesn't say anything. Okay, I think we have to declare some constructor for this. Now a constructor in Haskell is a function. And it has a special way of being declared. And you do this with the equal sign. And then we can declare a constructor for the myList type. And let's start with the empty list. So this is the empty list type. And if we compare this to Java, this would be myList with no arguments, something like that. Now if we reload and say browse to inspect what we have in scope, then we can see we have the type myList, which has star to star, and this means the kind of it is that it expects one type variable and then you get the full type. But more importantly, we have a data constructor here. So we have the constructor empty list. And if we call this, it will complain that it cannot show this, because showing things in Haskell is used with the type class show, which is something like a toString function. But we can investigate the type of it if we create and call this constructor. So with the :T again, we can inspect the type, and the empty list has the type myList of A. And in Java terms, it would just be myList of any type. Questions so far? Let's start, for debugging purposes, to implement the show class for the mylist type. And we do this by calling instance, or by writing instance. Instance of instance what? Well, instance show for mylist A. So show has a, can we call info in it? Well, yes, we can. Okay, so show has the definition of just show A. So it expects a type which has no more free type variables. So it cannot accept a type with the show instance now, which has some free type variable. Like we would have to get rid of the t for it to show. So we must add the a here. And now for the show interface or type class, it complains that we have to implement showsPreg, which is a little bit more complicated, but you will have to implement the show method function, not method, function. And we do this by writing in this where block show a equals, well, we don't know what it equals yet. And if we run into a situation in Haskell where we don't know what type we need to put in there yet, but need some more documentation or some more help with the type checker, then you can write an underscore and then any letter, usually you use H. And then your IDE will help you, or also the interpreter will help you. And in this case, it helps by stating that it found a hole underscore H, which should be of type string. So we could just put some string here, like hello world. And if we do this, then every time we want to print the list, it will just print hello world, which is not really useful. So the next concept we can use in Haskell is called pattern matching. And you do pattern matching on data constructors. And you do this by, there's two ways to do this. One way to do this is to use the case operator. So you could write case A of empty list, and then you can just write empty. So if our list is empty, we write empty, which is okay. Let's use empty list because there's a rule for the show instance, but we will see this later, hopefully. And if we reload now with :R, then we can just write empty list and it will print it for us. Now an empty list is not really useful. So how could we make another, or is there a way to put more things into the list? And there really is, of course. We haven't used this a variable here, this type variable. So this is, well, it's a placeholder for a type that is yet to be there. And we can declare a second constructor, so like an alternative way of constructing data. And this is done with the pipe symbol. And we could now create a constructor which is like cell A. So in this case, the mylist type is either empty or it is a cell for a list. Now cells for lists are not very useful because then we can only store one thing. But we want to make a list, so we have to store many things. And this we can do by saying it is the constructor has two parameters. And the next parameter is something of mylist A. So here we have a situation of a recursive data type. A mylist can either be the empty list or it can be a cell with some value of type A followed by a list again with values of type A. And the empty list is an inhabitant of any type in this case. And if we do this in Java, it would look like something like this. Value would be T value, I think. I'm going to make this a multiple lines comment. Yeah, this is how you can do multi-line comments, by the way. So bracket and then dash. Let's do proper Java, or at least more proper Java than this was. And to use this, we could have some private variable, private T value, and private myList T next. Something like this. And this would also be myList T next. And now I don't want to deal with null pointers, but we would have to have something like this. And then we say this value equals value and this next equals next. So this is how we would declare this data type we have here in Java terms. But it is used a little bit differently because, well, we will see this. We will see this. I'm going to open up another window so that we can view the Java way of doing this and also the Haskell way. And I'm actually going to copy all of this down to where we use it. Okay, so we can see that the case statement here, it says now pattern matches are non-exhaustive because we have an alternative constructor here. So we need some way to get the data out. And we do this by adding another case to our case statement. So we can either have the empty list, or maybe someone in the chat can help me. Okay, the second case is that we have the cell. So cell with some value and the next list. And this is how we can extract data now. And well, let's make it just write cell for now. And now in our interactive interpreter session, we can actually create lists now. So if we call empty list, it says empty list. If we make it a cell with 1 and then empty list, then it says, I didn't reload yet. Then it says cell. Now, but we know it's two elements long, so we can concatenate it using this operator here with the show of my list. Or let's actually call this next list. And now we have kind of, do you see how our data type is recursive? So it is either empty or it holds a constructor with a value that holds a value and then itself again. And this is like reappearing in this show implementation. And if we reload, I must not forget to reload, then we can see that it correctly prints that this list has one cell and then nothing or empty. And now, because it's recursive, we can add as many cells as we want. So we can now make it also longer. And if we print us that there are 2 cells, or, well, yeah, we can make it longer and add more things, and it will just grow. Now, a list that has values but doesn't print them when we ask it to is also not very useful. So we need to somehow make the list also show the value that it carries. By the way, this is string concatenation. More generally, it is monoid concatenation, but maybe at the end of the video we know what that is. But you can use this to concatenate strings for now. And well, this code won't compile. So before we could print the cells because we didn't try to print the value. Why would it fail in this situation? Let's look at the error we get. And that error is, well, kind of hidden by Emacs, so I will reload in the interactive interpreter. Because I am no Emacs pro, and it tells us no instance for show A arising from a use of show. Possible fix, add show A to the context of the instance declaration. And these kind of errors you get a lot. What it's really telling us is that, well, you asked me to call or to invoke the show function on the value, but I do not know if it's really printable. For example, you cannot print functions, but we can fix this. I just want to write it down here in Java as well. You can imagine the show type class to be like this. Interface show, where, oh, well, I'm getting mixed now. So the show interface has some kind of public string to string or show. So this is what we are trying now. Whoops. If I don't get rid of these things, I wanted to do it like this for indentation purposes. And in Java terms, what we are trying right now is to implement the show interface, but in order to do this, we must know that T can also be shown, which it cannot generally. We would have to write something like T extends show, I think. I think that's how you do it. And then it would work in Java. And in Haskell you can do it pretty cool. You can put a constraint on your type. So, in order to show the value or to print it, we must say that this A that we are talking about, that is the value type, that this can also be shown. So we say show A and then an arrow, an arrow. So this is sort of like implication, like logical implication. If show A exists, or if A can be shown, then we can show my list with the type A. So it's kind of like a conditional interface implementation, which is pretty cool. And let's see if it works. In our session, let's reload and yeah, print exactly this. And we can see that it works. Now the indentation is not so nice. Maybe we should comma separate it. Yeah, I think we can do this actually. If we now add a comma, it should, oh, before this one, of course. Then it's nicely formatted also for us. Any questions so far? Does it make sense? So this is all the code we have in Haskell, and this is some kind of example code for Java. Matter of fact, this is like public string show. I will be coding the Java stuff and maybe questions arise. Yes, we've implemented the linked list in Haskell. That's correct. We just did that. And we've also implemented the printing, but only if the underlying value can be printed too. So this will be like system out print line, right? I think that's Java. And then we have the plus operator, I think. And oh, I'm so horrible in Java. I'm only noticing this. Can you just... Oh no, we want to call the show method. Okay, the next thing we want to do is do something with the values. And let's do that. Let's say for a list of integers that we want to add 1. So we make a function. It would be plus value only the type stuff because value is of type T and is simple property. Would be plus value. Oh, cool. I wanted to exaggerate that this value thing also has to implement the show method, so that it's also of type, or also implements the interface in Java terms. So that's why I'm using the .show thing here. Something like that. I think that should work. And then have something like only if T has show. show implementation. Something like this. I'm really not super sure how you do this in Java. I'm pretty sure you can do this, but well. Things next dot show or something like that. Yeah, it would be of show of t. Oh, that's the thing. All right. Well, yeah. Java's just an example. I'm pretty sure there are people that can do Java better than me. Now, we have a little bit much syntax here, and there's a trick. We can shorten this function. We can shorten the case statement out of this. And this we can do by already pattern matching on the function invocation. So we can say show empty list equals empty list, and show cell, val, and next list equals just that. It's a little bit shorter. One line shorter. Actually not, because I'm going to put an enter sign here. New line. But you get the idea. It's a little bit more cleaner, I think. So this is like pattern matching at the function declaration level and not on the case. All right, now let's write a function which adds 1 to every element of our list. And we call this function add1 to list. And now here's the function definition syntax. It takes my list. Let's start with A, and then gives you back the same list but with 1 added. So add 1 to list A equals, what should it equal? We put a hole there. And then look at it again. Probably my buffer is too small because I've zoomed in a lot, and that's a lot more than when I program privately. But it says us, hey, I found a hole which should be of type mylist_a. Now we could just setify, say it's an empty list, and call it a day, but then we would just have a forgetful function, which would be pretty useless. What we want to do is, in a pretty similar manner, iterate on the values. And we do this again with pattern matching. If we get the empty list, then we give back the empty list, because we can not add 1 to nothing. If we get anything else than the empty list, so cell of val and n, or let's call this a common pattern you see in Haskell papers and something. It's that it's called x and then xs. Okay, so this is something Haskellers do, but everything comes down to your personal taste. I think it's very short and it matches like the stuff you find in other tutorials. So in this case, xs is again my list of A. And now it complains that it still needs to return something of type mylist_a, but we've already got one case done. And when we want to return something of type mylist_a again, then we of course have to construct a new cell. So it would be something like this. Access. Would this work? Would this work? No, it wouldn't. But we will see why. The problem here is that it assumes A to be just any type variable. It could be a number, could be a boolean, could be a function, could be again my list. Then we would have a list of lists, and all of these things could be in that A, but we want to add 1. So we can just make it an integer. So given mylist_int, it returns also mylist_int. And now there's a second problem. It's the second problem. It type checks, and we say that type checking probably works. Like if you program type checks, then it probably works. But can anyone from the chat spot the second problem that we have here? And the code compiles, by the way. It's perfectly fine code. I think we can even invoke this. We can invoke this. But there's a little bug. And that's more of the semantics of the function. The bug is, it will be very obvious if I write this again. Can you spot the bug now? We wanted to add 1 to list, with meaning add 1 to every item of the list. It must be everything. The question was access could be anything but my list, but it must be again my list because of the constructor. So we know that this is of type my list A again. The bug we have here is that we must call the function again on the rest of the list. So have this recursive. Probably a shitty question. So now it goes through the entire list from left to right. Let's try that again. And it adds to both elements. Here it only added to the first one, calls it a day, but now it iterates properly or recurses properly. So this is for adding 1 to our list. Now it would be very unfortunate if for every thing that we want to do to the items of our list that we would have to redeclare a function like this and do all the pattern matching and everything. Oh, yeah, that's also a good thing. Let's call this increment 1. Let's call this like increment list something. Yeah, adding, that's a good thing. That's good that you mentioned this. Adding is very ambiguous when talking about lists. It could be like addition, which I would call add, but also appending elements. Okay, so it would be very unfortunate if at each iteration through our list we would have to redefine a function of this type that does the pattern matching, does the actual magic, and then recurses. Like, this would be very tedious to do. So a trick we can use, because the only thing that is general or that we are really interested in doing is really this operation here. So the operation on the value. And we could make a function that invokes some other function on every element of the list. Let's call this function mapList. And it takes a mylist of A, or no, actually, it takes a function from A to B, so to some other type variable, and it then takes the input list, A, and ultimately gives you back the output list, mylist B. And mapList would have a signature like this, and the parameters would be something like f and axis. So something like that, right? Are there any questions on the type signatures? So this is how you define a function as a parameter. You put braces around it. If you leave the braces out, then it would mean something different. Then you would expect two parameters to your function. And in this case, with the braces, you just expect one parameter, or at least not two for both of these, but just one parameter that is a function. Okay, so this has two inputs and gives you back one output. So the last thing at the dash is the output. Okay, so now we have abstracted this kind of situation that we have up here, but we still need to somehow implement it. Any ideas for this? This is actually my list. If you have any ideas how this would be implemented now, if you can see something, that was the question. The map list or the increment would change to int because with map list you can now apply it to your entire list. Yes, that's correct. That's a master plan. The question, well, maybe I should start practicing formulating questions in a better way. The question was how this would be implemented, and as you said and correctly saw, it is essentially the same thing. So we have one case where it's empty, and in that case it stays empty, and we have one case where we want to operate on the value. So cell x and axis equals cell, and now f of x, and then map list with the same function f on the rest of the list. And as the chat correctly explained, it would just be map list of, the increment list would just change to map list add 1, where add 1 takes an integer and gives you back an integer. Add 1 of x equals x plus 1. Something like this. And it of course takes an input list and invokes my list with it invokes map list with the input list. So this is now for clarity. I will keep this for clarity. Except for this first one here, the add one thing. In Haskell you can define anonymous functions with a very nice syntax, and that's with starting with a backslash character. And the reason that they chose the backslash character is that it sort of looks like a lambda sign. So this would now be x to x plus 1. And then we can get rid of this add one helper function here. Now this works. And another nice thing that we have is something that is called point free style. And point free style you should not overuse, because it tends to make your things a little bit messy, but it also greatly reduces the amount of variables that you have in your code, and therefore also the amount of naming that you have to give to your variables, ultimately maybe leading to code that is faster to write, or faster to prototype at least. And the way you do this is if we inspect the type of this lambda expression that we have there, like backslash x, x plus 1, then it says, well, okay, numbers in Haskell are overloaded, so this plus operation, pretty much similar to this show thing that we have here. The plus operation is only implemented for things that satisfy the num type class. And I don't know every function that the num type class exposes, but I think one of this is plus. So essentially, numbers in Haskell behave more like interfaces, and you have to keep this in mind to digest these strange type signatures. Essentially, this lambda expression now just is of type number to output number, so int to int, for example. And we can shorten this. If we take a look at the plus function, plus is also a function, then we can see that it's kind of the same thing, but with one type variable more. So what is the type of plus 1? Which we have just seen there, because the plus function is just like any other function except of this weird signature, but you can add arguments to it. Maybe we will show this a little bit better. Let's define a function add, takes an int, takes two integers actually, and add x y equals x plus y. Okay. And now we can also define a function add one, which just takes one parameter, and add one of x, or let's be clear and call this y, equals add one y. And now we can get rid of the y here. And this is called currying. I think it's called currying in normal languages. And this is also type checks. So if you pre-fill an argument, then you get back the remaining thing here. And that's, well, internally, or the theory behind this is that this declaration thing here is write associative. So we could also write it like this. You can, the brackets are optional when writing from left to right. So every function in Haskell that takes more than two parameters can be made to or you can make a function from it that only takes one parameter if you just pre-fill one of these things. So if we now add or invoke this add function with a predefined parameter, then we get back the second chunk of the function, because essentially this thing is removed, and this is what is resembled down here in the add1 function declaration, and that is why we can just write add1. I will keep this here. No, I will just keep this here. So what does this tell us? In the end, we could have just written this one here with not a lambda expression, but just stating +1 and pre-filling one argument of the plus function with an actual value. If you don't believe me, we can try it. Call increment list on the list we had before. And it has incremented both elements. Matter of fact, we can even make it more shorter by removing the argument from the declaration here also. And this is the same thing, because map list, if provided with a first initial function, then gives you back all of this chunk here. So this is called like reducing the variables that you explicitly mention is called point-free style, and we shouldn't overuse it, but I mean in situations like this it's just so pretty, right? Okay, and here it complains about a variable that we have defined but not used. The way you turn this off, or well, the way that you don't get errors from this, is by replacing it with an underscore. And the underscore in pattern matching means anything else. Now we have a function map list. Let's try it out with something other than numbers. We could, for example, map list and append an exclamation point to every string in our list of strings. Hello and cell world, and then the empty list. And it has put the exclamation point behind every list element and printed it accordingly. This is pretty neat stuff, right? Now, what if we have a situation where we have a list of numbers and we want to add it to another list of numbers? So, addition with lists. And for this, we can use, we can try to use map list again. Let's call it add lists together. It takes a something like this. Actually, I have to look something up really quick. Which I don't want to show on screen because I don't want to spoil. Especially not the more experienced Haskell programmers we have in the chat. And I don't want to make a big mistake on stream. And I will tell you what I have looked up in a second. Okay, I'm trying to look up the applicative instance for lists so that I don't make a mistake here. Because I'm not sure if it zips. Because I usually use the bind thing. So it does zip. No, it doesn't. It doesn't. I think it doesn't. Okay. So yeah, add lists together. But this is a bad example. This is like zipping. So I'm trying to look up proper applicative. Applicative example. Okay. So it would be something like add each from left, something like this. Should be a simple example. And it, for every A in list A, B from list for every A in list A, it is added to B from list B. So this is not for every A in list A is added to A B from list B, and the results are gathered. Something like this should work. Okay, maybe I should go about this a different way. Let's call this apply each from left. Apply to each. This is good. This is a good name, I think. Apply to each. This takes 2 integers. So this is for every F in list A. B from list B is applied. Is it that? Yeah, this should be it. This should be it. This is sorry. I should have thought about this before, because it's kind of a weird situation that we have here. Now, let's imagine that we are trying to do something like this. So we have map list of a function plus 1 to a cell 1 and then the empty list. What's the type of that? What's the type of that? It's from num b to my list b. Okay, and if we just go this, it's of type my list a to a. Okay. So we have a list that, as we've talked about before, that pre-fills one argument of the plus function. One argument of the plus function is pre-filled, and we want to apply this list to another list. So, for example, we want to somehow make that, whoops, doesn't know how to print it, because you cannot print functions, that's why I'm complaining. We have a list of functions, and we want to apply each element of a second list to each function of the first list. So yeah, that's a better explanation. Each element from the second list is applied to each function from the first. And this is like such a it sounds like such a toy example. Like, why would you ever have this? But once you get more functional programming, then you really notice that you have this situation quite a lot. And for example, here we could now somehow we want to call 2 plus something and 1 plus something and do this for a lot of things. And we cannot just write the second list below this. So one empty list. This is not proper typed, because the map list function, once it has been given both its parameters, then it doesn't expect any more. So this is mismatch brackets, which is sad. We need one more here. No, we don't. Oh, at the back. So now we get this big error, which is not really helpful for us, because the type of map list with plus is, I had this before, right? Is num a, which is in this case int, to my list of functions. And we want to somehow apply every function from the left list to every value from the right list and gather the results. And the way we do this is by using pattern matching again. So we have the case where we want to add the empty list to anything else. And we can just write to x. And that's x. No, that's empty list, sorry. And then we have the case where we want to add apply to each cell. Now we have f and f's to another list. Well, x, let's start with x. Or no, to another value, really. To cell x axis. And that is now cell f of x, like this. It's a little bit contrived, really. I'm wondering if we should really try this. And it now apply to each of with the rest that is applied to each f's and x. I think this should work. Couldn't match type. I'm too stupid for this. F of x. Well, we want to have this. Oh shit. Really should have thought about it. In list syntax, it's so easy. So we have one cell or one list with functions and one cell. And we want to use the remaining functions on this cell. So we would have to we have one invocation here, and the remaining ones should be, well, it's just a singleton cell, really. So this is from cell and then empty lists. Or is it not? Oh no, it's not. It's not. It's from cell with access. That. If we do it like this, then I think we are zipping the lists, and this is a different semantic. So either list that is shorter would be, we would just lose information. So if we have fewer functions than values, then we drop some values. If we have fewer values than functions, then we drop functions. And we want to really apply each value to each function. So we have one f of x, and then we will have to, I think we have to pattern match again. Do we? Man, I should have tried this before. It's been so long. It's been so long since I was forced to do these kind of things myself. We invoke cell of f of x, and then we call apply to each f's to x's. The problem is this thing here will eventually be empty. But it can only be empty if the left one is also empty. So it would be like such a bold statement. Let's debug guys. Let's just debug. Let's call let test list or let functions equal to cell of 1 plus and then cell of 2 plus and then empty cell. Map list here. Oh yeah. We can use map list. That's correct. Awesome. Okay. We should do this. Yeah, that's a good idea. So we can use map list of f with the rest, essentially. So that's x. Map list f with x. And then we will, oh, this is my list. Let's call it my list. But we have to make it recursive also. So this would be a, we already covered the empty case, I think. We have to implement some kind of concatenation. We have concatenation already. Oh yeah, we have concatenation already. Because of the constructor. We can concatenate with the constructor cell. So that works. So that's a cell of, oh no, maybe we have to pattern match. Case map list of empty list. That's always an empty list. Hold on. This is always empty. We use map list of f to on my list. And then we want to also deal with the rest, the remaining f's, right? So just call apply to each on the result of map list. Okay, let's do that. Apply to each f's on map list. I think that's it, man. Thanks for the help. So yeah, let functions equals cell. Empty list. Empty list. What's the type of functions? Well, it's a list. And then apply to each of functions with cell. Let's try one and empty list. It's empty list, huh? That's not good. That is not good. Because we need some kind of accumulator, maybe? Apply to each. I think this one here is the error. But we need to somehow extract the values. Yeah, exactly. We need some kind of accumulator, maybe. That's why I thought we would, or we could somehow concatenate these things. Because I think, yeah, we're really close. And this is what happens when you get confused from your own code and don't try things before. So my list into int, my list int, my list. And here we already have map list. Essentially what we're trying to do is for each of the left, take for each of the right, and apply these, and put them out again. And I want to find the, well, less confusing solution to this. It should return X. Let's try that. I think. Yeah, it could be that. Could be that. Oh yeah, functions is 1 plus. And that is 1. It should be 2 and 3. Should be 2 and 3. That is returned here. Why does it return 4 though? What's the deal with that? It somehow called both functions and didn't append them. Yeah, it always adds to the first cell, which is also not quite what we want. What are we doing, man? We are never concatenating, and that's a problem. At least I think it is. No, it's not. It's not correct. It should have been. It should have been 1. I mean 2 and 3, and then empty list. Yeah. That's what you get. Let's write a helper function. MyList A, and then MyList A gives you back MyList A. So this is for concatenating things. A's, B's, or actually X's and Y's. And concat of empty list Y's equals just Y's, and concat of cell cell and X X's Y's is equal to a cell of X and concat X's Y's. I think that should work. Oh, we have to list concat. That is not list concat. Cell 1, cell 2, empty list, cell 3, cell 4, empty list, 1, 2, 3, 4, empty list. Okay, we are getting somewhere. Yeah, at each function application that should be returned. So this is now concat the blah. Yeah, this is map list f my list concat or list concat with apply to each f's my list. Let's try that. Two, three. Why does it still have the one there? Oh, that's because of this. Okay, and let's also extend this. Empty list a equals just a. Let's call this axis. Okay, now we have a canonical situation here. Oh, I used some syntax which we didn't discuss before. If you put a function in backticks, then you can use it in infix style. Yeah. So each element from the second list is applied to each function from the first, and the results are gathered. This is now what we have, basically. And the concatenation thing is just to get there. Probably not the prettiest solution, but it works. It works. And it will demonstrate where we are going later. And, well, you might be wondering now, why would we ever want such a weird function? The cool thing is that it is perfectly, like, it synergizes with the map list function in such a cool manner. If we call, for example, here map list with +1 on some list, cell 1 and cell 2, empty list. I screwed with the brackets. Then we get 2 and 3. But if we just say plus, then we get back a list of functions. And now we can use this also with apply to each and construct a second one. Cell 2 and 3, or let's use 8 and 9. I think that will be convincing. Oh, cell 9 empty list. And then we can do arithmetic in a very cool manner. So this is a function that we will use a lot. So we first invoke map list with just the plus, and then all the cells pre-fill one argument of the plus, and then we can invoke each of the cell of the other list's values to the first list of multiple functions, and then we get back all the results applied. Let's double check that it's correct. We add 1 to 8, then we add 2 to 8, which is 10. Then we add 1 to 9, which is 10. Then we add 2 to 9, which is 11. Okay, so this is a really cool function, and we're going to be using it. Now the second thing is, what if we call map list on not just plus, but on something like this? x, and then x, we want to x plus 2, and then another cell with x plus 3, and then the empty list. And then mess with the brackets. So we have this weird situation. And it actually type checks. That's cool. We didn't expect this. And what we have here now is, well, some empty list in between. I will demonstrate what the problem is here with some brackets. So this is show a equals bracket here, then bracket there, oops, of show tick a, where show tick, well, show tick is essentially that thing here. Show tick. Let's indent this a little bit. And then you will see the problem much easier if I also indent the lower side of the code here. Yeah, this shows the problem. We have here one list, one big list, and this big list has small lists, 2 of them. And it can have very many of them. Like this. And we just make it deeper and deeper. So now we have 3 lists in one list. And we need some way to flatten them. So what we have here is flat map. And flat map takes a function from A to my list B, and then a list, my list A, and ultimately we want to have my list B. So that's flat map. I think flat map is already a function, so let's call it flat map list. And this is not the situation that we have right now. If we take a look of what this type is, it's a nested list. So my list of my list A. And this is not what we are intending. We want to make a list that is just the values B. So how do we do this? Well, we can again concat, essentially. We can just concat. If we have empty list here, oh no, we always get some function f, and it produces values of type B. And then we have the list. And yeah, that's kind of it, right? We have a function from A to my list B and then a list of A's. So we want to, for each list of A's, invoke the function that we get and gather the results. Which means, let's put a typo here, and will tell us that it expects my list B. Well, we can map list. We can map list. Again, I'm very, I really appreciate help from the chat. Somehow we need to extract a value of the second one and put it into the function. And we can do this, I bet. Basically, we need to map list, but we need to map list with an extra step. And that step is to flatten the list invocations. So to flatten the structure that we have from calling f. So we need to somehow flatten list. And flatten list is some function which is of type myList of my list b to just my list b. So essentially it just concatenates it. Flatten list of empty list. Can we do this in one go? I think we can somehow. We already have the list concat. Yeah, we already have that. So essentially it's just a matter of pattern matching. If we call it with the cell of some type, cell of empty cell, then it's just access. If we call it with cell of some cell x and access, oh, let's call this y's. Then it's a cell of x and then why doesn't this type check? Oh, it's not empty cell, it's empty list. That's what we said. We called it. Then we take one, and now it's going to complain, hey, I didn't expect this type. So this is now just one cell with follow-up access. But access, or is it really? Yeah, but access is also flattened. No, it's not. Y's is also flattened. Is it with the cell of access? No, it actually should be flatten list access. Like that? Does it work? Don't think it does. Can I construct the infinite type? Okay. So flatten list of empty list equals empty list. We have that. If the first one is empty, then it's just the rest. If the first one has something, then it's this stuff here. Flatten list. That. Is that it? No, we don't recurse. axis, list concat, nice. I think this should be it. No, it's not. Why is it complaining? Why is it complaining? Okay. So we have one x and we extract it upwards. And we want to concat it. Oh, hold up. Let's make it a cell. Just concat one cell with empty list. And then flatten list axis like this. Oh no, wait, this stays. This stays. And this is just flatten list. Nice. This should work. And we can just call this X. Get rid of that case also. Yeah, that should work. At least I hope it does. Let's make it a top level definition and try it out. What did we have? This here, right? Yeah. So we have this list and we want to flatten it. Flatten this, that. Get back, well, what did we expect? 3, 4, 4, 5, 5, 6. And what do we get? 3, 4, 4, 5, 5, 6. Yeah, perfect. Let's investigate the types. If we so this is again the function that takes an x, adds 2, and then also adds 3. So it has a result type of type list. And we provide it with 1, 2, and 3. So, yeah. So the inner function that we use map with gives you 2 outcomes, and we use 3 parameters, so we get 6 outcomes. And if we just use map list, then it's a list of lists. If we use flatten list, then it's just one list. Let's look at the type of this, and it's just my list B. And if we check out how many elements we have, then it should be also 6. 1, 2, 3, 4, 5, 6. Awesome. And well, flat map in this situation is just exactly what I just described. So flat map list already does that. So with flat map list, you give it an A that results in a list of B's, and then you give it a list of A, and then you get back a list of B. Are there questions about this? Because, well, this is a rather complicated type signature. But in the end, this is just a sort of like a for each situation. For example, what we can do with this is make coordinate systems pretty easily. For example, we have 1, 2, and 3. And then we get back, or then we use flat map list 2 and 3. But let's not use plus, but comma. Then we get some very cool cells out. So this is also, let's also use cell x1. Then these here. So now we have like a Cartesian multiplication, okay? So let's say Cartesian grid takes an integer and another integer, so like width and height, and gives you back my list of int, like that. Cartesian grid of width and height equals flat map list. Or actually we need to construct some helper function. Let's make a helper function to create a very big list. Create sequence. Let's call it sequence. Takes a list, an integer, and gives you back my list A. And create sequence of I equals, hold on. My phone is loud. Create sequence of my list I equals a cell of I followed by create sequence I minus 1. And create sequence of 0 equals cell, well, no, it's the empty list. Now we have some function to create cool lists pretty easily. Why does it complain about line 77? Oh, I didn't write undefined yet. So, why does it complain? Oh, well, this is a list of this is int. This is int. So create sequence 8 or 9. Gives you 9 to 1. Actually, I would like it to start at 0. Right? This is kind of weird. So let's have this at I minus 1. Yeah, like that. So yeah, if we create sequence of 9, then we get 8 to 0. And we could, for example, make a chessboard with this. If we say flatten list, flat map, or first we need to create two sequences. Create sequence width and create sequence height. And we want to invoke for each sequence the flat map list, or actually the apply to each. I think that's enough for a chessboard. Then we can make the x, y, those two x and y, map list. Just like that. It's complaining because expect type mylist int, actual type mylist int. Oh yeah, it's complaining because create sequence. Okay, it's totally fine that it complains. Let's say let tiles x equal create sequence y width, and tiles y equal create sequence y height in, and now we want to somehow enumerate them. And how would this work? Well, it works by using flat map list, which gets the x coordinate on some list A, which is tiles x, and then we use a map list. Oh no, actually we use flat map list again. Yeah, I think we use flat map list again. Why? Y to flat map list. Oh no, x and y. Flat map list on tiles y. I think this should give us like a chessboard. If I'm not mistaken. Of course. Oh, I forgot an S. Okay, and this now expects a list, so let's not use flat map list, but just map list. Did I not call this map list? Yes, I did. Okay. And Cartesian grid of 8 and 8 gives us a chessboard. Well, something like a chessboard, okay? So we have 7, 7, 7, 6, 7, 5, so on. Like from 7 to 0, from 6 to 0, from 5 to 0. And if we now add 1 to each of them, let's actually do this. Let's say, we can do it here already. X plus 1 and y plus 1. And we get a chessboard. Indices. And if we write it with this syntax again, then I think it's also pretty neat. And well, now we have done all of this to implement our own list type. Of course, we had some problems. The next thing that we can do is to implement an optional type like we have in Rust. So data option. Then Rust is called, what's it called? I think none. Or is it none? Let's look at the Rust wiki. That's docs rs. There's option, right? Should be called option. No. The Rust. Wait, this is packages. Docs Rust. Rust lang. All right. Where's Rust prelude docs? If I want to get the library, the standard library, there we have it. Rust prelude. There should be optional, right? Option. Sum. Okay, it's called sum. Okay, so in Rust you have the option type, which has two constructors, sum and none. Sum A. Option A, none A. And I'm going to make this pretty quick. We want to have a function map option. Takes A to B function, then some option A, then some option B. Map option, if provided a function and nothing, then it returns none. Map option provided a function and sum A gives you back sum f of A. And then we have apply option from A to, that's two options. One option, A to B, then one option B. Apply option, F and none is none. Oops, I mean anything. This case also. And apply option of sum F to sum X equals sum F of X. And then we have, well, flat map option, right? So it's an option, no, it's a function from A to option B. So something that could fail, some function that could fail, then some option A, and then some option B. Flat map option ignores its first argument in case it's none. Then it stays none. And in any other case, it just applies that. Why does it complain here? Oh, because I forgot the second option. Does this make sense? Was it too fast? It was probably pretty fast, but that's what you have for optionals. And now, if we look, for example, at map list, I'm going to put this here as a comment. And we have apply to each at apply option. And also flat map list. Then we can see that the only thing that differs is this wrapping type. So there is map list and map option. And map list takes A to B and my list of A and my list of B. And map option takes A to B, option A and option B. And well, it's a very similar signature. The reason that this is so similar is because there is a thing called a functor in Haskell, in the Haskell standard library. Functor. Let's look at what a functor is. Info functor. A functor is a data type that wraps another data type. So you have one free type variable, which is the case for list and option. And then you get a function from A to B, ultimately resulting in that data type, but with a different inner value. This is exactly the case for map option. So we can make our option thing an instance of functor. Instance functor option where fmap equals map option. So fmap is exactly that. And we can also make our list an instance of functor. Instance functor my list where fmap equals map list. So this is a cool thing to have in mind. And the nice thing is fmap is so widely used in the standard library, you can never use another library that doesn't somehow implement fmap. So this is like a really common pattern to have things that can be mapped over. And functors, or fmap precisely, there is the function fmap of that type, and it has a type alias, which is this pointy bracket, dollar, and then closing pointy bracket. And it's the same thing if I put brackets around it. So that's also that. And we can use it in the same way. So we have the sequence list function, this one, or could we just call it sequence? What do you call this? Create sequence. Okay, so create sequence 8. And now that we know that it's functorial, we can add 1 to it with the same, if I reload, holy shit. We have to put the function first, +1, and it's the same as if we would have used map list. The same goes for option. If we create something with sum 8, we have to specify this is an integer. Oh no, we cannot print it yet. So we have to derive, create instances. Instance show A, option A, where show none equals none, and show sum A equals sum with show A. I think that should work. Why is it, what does it say? Not visible. because I put the braces around it. Oh, option, I mean show. Sorry about that. And that is show option. Okay. Yeah, it's getting late. So that's now there we have it. After all the type foo, we can now add two lists, like here, and also two option types. Same thing if that was empty or if the list is the empty list. So this is all allowed now without errors, which is pretty cool, and this allows a common interface. So fmap is a beautiful function for functors because they have so much in common. And there's also the second thing that's called applicative. So instance applicative option where, and now applicative has this weird function name that is with the star, but it's exactly our apply option or instance applicative of my list where this thing equals apply, or no, for how did we say this? Each apply or apply each left or something? Apply to each. That is apply to each. But applicative also needs a second function to be implemented, which is called pure. And pure takes an A, and then you need to wrap your data type in it. So pure pure of A in my list equals cell, obviously, cell and then empty list. Like that. Why does it complain here? Did I mess something up? Oh, we only specified it to int, but we could use any other, really. Like here, right? We don't have to only use ints. We can go from A to B, then get a list of A, give back a list of B. Because why not? We just said it should be ints. It can be anything. So this works. And the last one, which is most of the times the least easy one to get for new Haskellers, is the monad type class. And there you have to implement the bind operator, but that is really just a flat map option. Like this, I think. Wait. Flat map option. Where's the complaint? A to option B with option A0, expected type option A to option B, option B. Oh, I flipped the arguments. So this is the signature. Let's just use the flip function for this, because it's a little bit annoying to write it like this now. The flip function, by the way, takes a function, flips the arguments. So let's look at the type. Takes a function with two parameters, A and B, which ultimately lead to C, and then returns a function that takes B and then A and then gives you a C. So it just flips the first input parameters. Okay, and same for my list. where equals, whoops, where all right, just like that. Now, the cool thing with monads especially is you get something that is called do notation, and we will see this. Do you remember the Cartesian grid function here? This one. So what we can do with monads is use the bind operator. So Cartesian grid monad, let's call it that, equals int, it takes two integers, gives you back my list of int and int, like that. Cartesian grid, let's call it m. With height is equal to create sequence width bind create sequence height bind return or pure. We need to get values out of these, x and y, pure x and y. So this is the alternative kind of way of writing this in this situation. Let's try if it works. Cartesian grid m of 8 and 8, and we get back a chessboard. Something similar at least. That's also +1. And for monads, because they are so common, monads are so common, we get special syntax for them. Let's call it with mtick, and it's just the same signature. Width and height, and then you can use something that is called do, and you get this special for monads called create sequence width, and y is our create sequence height, then pure x and y. So this is the alternative way of doing these things, either with the bind operator or the flat map or just do notation. The code gets smaller and smaller. The thing is, I've used the word pure here because we implemented the function pure, which in case of lists is just to create a list with just one element, so a singleton list basically. But monads export a second function, which is there for historical reasons. This applicative thing, it came back, it was implemented later. And the function is called return. And return is in most contexts the same thing as pure. But if we write it like this, then the code looks much more like what you're familiar with as a programmer. And ease of use is all that we want. And this little code creates a Cartesian grid of width and height. So, for example, a chessboard or I don't know, some world map for some, I don't know, game like Terraria or something. So this is DO notations. And these are some examples of monadic structures. There's tons of them. For example, you could have a function or a data type that takes a value and then functions that operate on the value or that at least read that value. So for example, some global environment for functions, and that thing is called the reader monad. And the reader monad is just that. It takes functions and provides these functions with a global environment that they can read from. For example, your application configuration. The other thing is the state monad, which allows you to have, well, state in functional style. So what you're familiar with, that you'd have a variable and that you add one and expect on the next steps to have it incremented. That's what you can do with the state monad. And there's also the writer monad, which allows, for example, for logging of applications, where you have a function that is called, I think, put, and you put, for example, something, a string, and then on subsequent calls to it, it appends to the string that you're logging to. But all of this in a very transparent manner, where you really don't have to deal with it so much and don't have to be explicit about these kind of things happening and contexts being carried around. Just like in here, where we really have an easy way of writing a code that essentially creates a chessboard. And there's tons of many more monads. There is the monad transformer library, which takes one monad and another monad and combines their superpowers, which we will talk about. But I think Functor, Applicative, and monad are the most important ones. And next Monday we will look at the I/O monad, which will allow us to get input and output. But on Thursday we will look at parsing IRC data from the Twitch API using ettoparsec, which is also a monad. And if you watched this video and understood some concepts, then you should be prepared to join us on Thursday. And I'm sorry for the little brain lag we had at the Applicative, and big thanks to the chat for helping me with that. I think it was here. Yeah, the apply to each. This pretty much took me out of focus. But thanks again to the chat for help. And we will see each other on Thursday, where we are going to parse the IRC data from the Twitch IRC with ettoparsec, which is monadic. See you then.